Hello Calc 3 and welcome back to another video. So in this video, I'll just be covering the first half of section 15.8, which is the last section for chapter 15. And section 15.8 more generally is covering substitutions for multiple integrals, so either double or triple integrals, but in this first half, I'm only going to be talking about substitutions for double integrals. And in the second part, that I upload sometime later today, then I'll talk specifically about substitutions for triple integrals. So in this section, we look at applying coordinate transformations to evaluate multiple integrals using substitutions. So right off the bat, you probably don't know what I mean by coordinate transformations, and that's okay because I will define them and describe them a little bit further down in the video. But ultimately, the goal is to use these transformations to take complicated integrals that pop up and convert these integrals into integrals that are much easier to evaluate. So broadly, the goal of the video is to build up a methodology that allows us to take difficult integrals and convert them into integrals that are easier to calculate. Okay, so let's build up this notion of a coordinate transformation and then talk about how it relates to the integral over a region or the double integral over a region. So remember back in section 15.4, we built up the notion of a double integral for functions in polar coordinates and regions given in polar coordinates. And it turns out that this transformation from Cartesian coordinates into polar coordinates is really just one particular instance of a much more broad and general idea. So we'll talk about this more general idea and how we can apply transformations that go from Cartesian coordinates to other kind of coordinates that don't have names. So not even just spherical coordinates, but you'll see what I mean below. So let's let G be some region in the UV plane where U and V give some coordinate system. So U and V are just variables and we set them up into a plane so that the U is going where the x-axis would typically go in our plane and the V is going where the y-axis would typically go in our plane. So we can pick any point inside of that plane and represent it as a point with coordinates U and V for some U and V. And we can call that region in the UV plane G, and so it's that region inside of yellow that I have in the diagram here. And here's the important part. We can talk about transformations, coordinate transformations, that map this region G into the Cartesian XY plane. So we let G of UV and H of UV be transformations, or really just functions, but you can think about them as transformations too, that take points UV in the region G inside of that UV plane and output points XY inside of the Cartesian XY plane. So you can see that in the diagram here, that point UV is going to be mapped to the point XY inside of the region R in the Cartesian plane. So these transformations, if you want to think about it pictorially, these transformations are taking our region G in the UV plane and they are morphing that region G into the region R. So we're taking points from the region G in the UV plane, we're mapping them through these transformations, and the transformations are outputting points inside of the region R. Okay, so we also assume that this transformation defined by G of UV and H of UV is 1-to-1 on G. So what I mean by that is that if you take any point XY inside of the region R, like this blue point that I have notated, then there's only going to be one point UV over in the region G in the UV plane that gets mapped to that point XY. So this is kind of a technical condition. For the most part, when it comes to calculation, you can just kind of forget it, but it is something that we need in order for some of the theorems that come up later to be true. So we call the region R in the XY plane the image of G under the map, under the transformation given by G of uv and H of uv, and we call G the pre-image of R. So these are definitions just to remember. So we have our transformation, it's going from the UV plane into the XY plane. The image of our region G in the UV plane is going to be the region R, and G is going to be called the pre-image because it's the region that we have before we map into R. Okay, so if f of xy is a function given in x and y, then notice that we can also write f as a function of u and v using this transformation that we have above. So x is given as a function of u and v. X is equal to g of uv. So we can substitute g of uv for x, and we can substitute h of uv for y. And once we do that substitution, now we've given the same function f, but we've given it in terms of the coordinates u and v. So these points are being taken from the uv plane and then mapped through the transformation and then mapped through the function f. And once we notice this, it makes us wonder, so how does the double integral of f of xy over the region R in the xy plane here relate to the double integral of f of g of uv, h of uv, over the region G in the uv plane? So we're taking points from G in the uv plane and we're mapping them over to the region R in the xy plane and then mapping them through the function f. And I want to know, how does the integral of f viewed as a function of u and v over this region G in the uv plane relate to the integral of f as a function of x and y over R in the xy plane? And the relation is actually going to end up being quite nice. And that's really the fundamental discovery of this whole section, is that there is a relation between these two things. So importantly, before we get to that relation, we have to define what's called a Jacobian. And you'll see why we define the Jacobian a little bit further down. So the Jacobian of some coordinate transformation given by x is equal to g of uv and y is equal to h of uv is given by, or defined to be, the determinant of a 2 by 2 matrix where each of the entries is the different partial derivatives. So the first entry is the partial derivative of x with respect to u. This entry is going to be the partial derivative of y with respect to u. Up here we have the partial derivative of x with respect to v and the partial derivative of y with respect to v. So if we wanted to calculate the Jacobian, we're going to evaluate each of these partial derivatives that's appearing inside of the matrix here, and then we're going to take those partial derivatives, put them into a 2 by 2 matrix, and take the determinant. And remember, using the formula for the determinant of a 2 by 2 matrix, this will give us partial x partial u times partial y partial v minus partial y partial u times partial x partial v. So this is another way that you could write the Jacobian, but it's probably most beneficial to think of it as the determinant of this 2 by 2 matrix consisting of the different partial derivatives. So again, the Jacobian might seem a little bit strange to define, but the reason that we define the Jacobian is simply because it's pragmatic, because the Jacobian pops up when we're relating the two integrals between the function over the region G in the uv plane and the function over the region R in the xy plane. So the Jacobian is going to help us relate these integrals. You should also note that another notation for the Jacobian is just j of uv is equal to this partial xy over partial uv. So that's another way that we could notate the Jacobian, just in case you see that in the text. And note that the Jacobian, geometrically, if you want to kind of build up an intuition for what this is doing, it's measuring how much the transformation is expanding or contracting around a point uv in G. So if you have some region in the UV plane and you pick some point, and then you pick a region around that point like this, and now you're mapping this region over to some region R in the XY plane. The question is, what is that transformation going to do with this whole box surrounding that point UV? And sometimes the transformation is going to expand that box, make it bigger. Sometimes the transformation is going to contract the box and make it smaller. The Jacobian geometrically is telling us at different points how much the transformation is expanding or contracting the space around my point UV. And understanding this geometric interpretation of the Jacobian really isn't important for the calculation. It's just in case you're interested. So if the Jacobian is greater than 1, then the transformation will be expanding around this, expanding the space around the point UV, and if the Jacobian is less than 1, the transformation is going to be contracting the space around UV. And this has to do with, if you've taken a linear algebra course, then the determinant of a matrix for a linear transformation in some way describes how much the space is being stretched. So it'll take the area of say a parallelogram formed by basis vectors and show you how that area is changed once you go through the transformation. And you can think about that as an expansion or a contraction of space, but again, that's not really important to Calc 3, just in case you're interested. Okay, so once we have this notion of a Jacobian, we can actually write the relationship between the integrals from before that we were interested in. And this is the fundamental finding of this whole section, very powerful. So suppose that f of xy is some continuous function in the variables x and y, of course, over the region R in the xy plane. And we can let G be the pre-image of R under some transformation where x is given by G of UV and y is given by H of UV. So here we have a transformation that's going from the UV plane into the XY plane. And we assume that this transformation is 1-to-1 on the interior of G. So again, you don't have to think much about the fact that it's 1-to-1, but it is necessary for this to be true. As long as G and H have continuous first partial derivatives within our region G, the pre-image, then we can say this relation between the integrals from above. The integral of f of xy, or the double integral of f of xy over the region R in the xy plane, is equal to the integral of f of g of uv h of uv. So here we're writing the function f as a function of the coordinates or the variables u and v multiplied by the absolute value of the Jacobian du dv over the region G. So now we're talking about the region G, that's the pre-image of R in the UV plane, and this gives a really nice relationship between these two different integrals. And the reason that this is important is because sometimes I can find transformations, x is equal to G of UV and y is equal to H of UV, such that I can rewrite my original integral as in the form of this second integral here, and this second integral will become much easier to evaluate, either because the region G becomes much simpler and we can find limits of integration that are a little bit easier to calculate, or because when we view f as a function of u and v, f becomes a more simple function. So the Jacobian gives us a way to rewrite the integral over R as an integral over the pre-image G. And this is why we define the Jacobian in the first place, because it's pragmatic. It gives us this relationship between the two integrals. Okay, so let's move on to our first example then. I think that your book actually starts out with a perfect example to introduce this, because we're really just showing that the derivation for the double integral using polar coordinates from section 15.4 is just a particular instance of this more general method here. So we use this more general method to derive the integral in polar coordinates. Okay, so we want to find the Jacobian for the polar coordinate transformation x equals r cosine theta and y equals r sine theta, and write the Cartesian integral, the integral of f of xy over the region R, as a polar integral. Okay, so let's start out by finding the Jacobian of the transformation first. So again, the Jacobian is going to be the 2 by 2 matrix where we have partial x with respect to r, partial x with respect to theta, and then partial y with respect to r, and partial y with respect to theta as the different rows, respectively. So if we take the partial derivative of x with respect to r, we get cosine theta. That's why it's popping up here. If we take the partial derivative of x with respect to theta, we get negative r times sine theta. If we take the partial derivative of y with respect to r, we get sine theta. And if we take the partial derivative of y with respect to theta, we get r times cosine theta. Now we can take the determinant of this 2 by 2 matrix, and we get r times cosine squared of theta plus r times sine squared theta. And then we can factor out an r, and cosine squared theta plus sine squared theta is just going to equal 1, and we're left with just r. So the Jacobian for the polar coordinate transformation is just equal to r. And hopefully you're starting to think, oh, I can see why the equation for the double integral in polar coordinates is what it is. So if we take the absolute value of the Jacobian of r theta, then this is going to equal the absolute value of r, because we just said the Jacobian is equal to r. But since r is always greater than or equal to 0 when we're integrating using polar coordinates, the absolute value of r is just going to be equal to r. And so, using the theorem that we just got from above, the double integral of f of xy over the region R is equal to the double integral of f of r cosine theta, where r cosine theta is being substituted for x here, and r sine theta in the second component here being substituted for y, times r over the region G. And if you would go back to section 15.4, this is exactly the equation that we found, relating the integral in Cartesian coordinates to the integral in polar coordinates. So again, the idea from section 15.4 is really just a particular instance of this more general methodology here. Okay, so now let's move into an example that's in unknown territory. So this won't have to do with polar coordinates or spherical coordinates. We're going to just use this method that we just developed here. So let's say we want to evaluate the iterated integral where we have the integral from 0 to 4 of the integral from x equals y over 2 to x equals y over 2 plus 1 of 2x minus y over 2 dx dy. And we want to evaluate by applying the following transformation. So the transformation is that u is going to equal 2x minus y over 2, and v is going to equal y over 2, and integrating over the appropriate region in the uv plane. Okay, so the first thing that we're going to want to do here is sketch both of our regions R and then G. So R is going to be the region corresponding to this double integral in the xy plane, and G is going to be the region in the UV plane that is the pre-image of R. Okay, so let's start off with just sketching the region R, and I should probably put that this is the xy plane here. So we have that the upper limit for x is going to be y over 2 plus 1. So we have the line x equals y over 2 plus 1, but we can make that look a little bit nicer and just say that this is 2x minus 2 equals y, and that's easier to graph as a line. We also have that x is equal to y over 2, which just implies that y is equal to 2x. So we take both of those lines, 2x minus 2 and 2x, and we plot them in the xy plane here. So we have y equals 2x minus 2 in red, and we have y equals 2x in green. And we also know that y is going to go from 0 to 4. So we can put in purple lines representing y equals 0 and y equals 4, and then we can color in that region. So that's the region of integration R in the xy plane. And now we want to use our transformations, this u equals 2x minus y over 2 and v equals y over 2, to ultimately give us what g is going to look like. So we want to have a definite relation between x, y, and u that allows us to say what happens to the lines y equals 2x and y equals 2x minus 2 inside of the UV plane based on this transformation here. So again, we have that u equals 2x minus y over 2, which implies that 2u is equal to 2x minus y, and we can do a little bit more algebra here. So 2u plus y over 2 is equal to x, and u plus y over 2 is equal to x. And remember that v was given as y over 2. So this tells us that u plus v is equal to x. So that's one of our transformations where we're giving x as a function of u and v. So I have that circled in purple here. And after we have that, then we can easily find here that y has to be equal to 2v. So now we're giving y as a function of u and v. So y equals 2x will be transformed to another line inside of the UV plane. And to do that, we're going to apply these transformations that we have here to the line y equals 2x. So we take y and we plug in 2v, and we take x and we plug in u plus v. And then again, we do some algebra and we end up finding that u has to equal 0. So that line y equals 2x, the pre-image of that line under the transformation x equals u plus v and y equals 2v is going to be the line u equals 0, which I now have in green. So you can think about that as, oh, well, the green line from the xy plane is corresponding with the green line in the UV plane that I now have drawn. Then we can also look at y equals 2x minus 2. And again, we do the same thing. So we plug in 2v for y, and we plug in u plus v for x. And doing some more algebra, we find that this corresponds to the line u equals 1. So the red line, y equals 2x minus 2 from the xy plane above, is going to transform to the line u equals 1 in this UV plane, or the red line that I have drawn. And now we want to see what happens with the lines y equals 0 and y equals 4. So again, we write y as 2v and then solve for v, and we get v equals 0 and v equals 2. So the line y equals 4 from the xy plane corresponds with the line v equals 2 in the UV plane, and the line y equals 0 from the xy plane corresponds with the line v equals 0 in the UV plane. And again, we can color in that region that we now have in the UV plane, and this is going to be the region G. So hopefully you can see that the region in the UV plane now under the transformation is going to be easier. It's going to be easier for us to find limits of integration over this region than it would be to find limits of integration for the region R in the XY plane. And this is one of the benefits of using these transformations. So next we want to calculate the Jacobian, and then after we have the Jacobian we can finally set up our integral. So for the Jacobian we need all of the different partial derivatives. So we have partial x with respect to u is just going to equal 1 because x is equal to u plus v. Partial y with respect to u is equal to 0. Partial x with respect to v is equal to 1. And partial y with respect to v is equal to 2. So we have all of our different partial derivatives. We take the partial derivatives and plug them into the corresponding 2 by 2 matrix, and we take the determinant of that 2 by 2 matrix and we get 2. So the absolute value of the Jacobian is just going to be equal to 2. And finally, at this point, we have enough information to rewrite the original integral using our coordinate transformation. So we have our original integral over here on the left is going to be equal to the double integral evaluated over this new region G in the UV plane, where we write our function 2x minus y over 2 as a function of u and v multiplied by the Jacobian, which is 2, and then we have dv du at the back end now. So our limit of integration for u is going to be 0 to 1. So you can see that just from looking at the region G in the UV plane immediately. And the limits of integration for v are going to be 0 to 2 for the region G in the UV plane, which hopefully you can also see that. And then we can take u plus v and substitute it for x, and we can take 2v and substitute it for y inside of our function. And so ultimately we get the integral from 0 to 1 of the integral from 0 to 2 of 2 times u plus v minus 2v over 2 times 2 dv du. So this is another way to write the integral now using our coordinate transformation, and now we can just evaluate this, this integral here. So it ends up being the integral from 0 to 1 of the integral from 0 to 2 of 2 times u dv du. And then we take the inner integral with respect to v. We get 2 times u times v evaluated from 0 to 2. We can plug in a 2 for v, and we get the integral from 0 to 1 of 4 times u du. And again, we take the integral with respect to u now, and we get 2u squared evaluated from 0 to 1. And this will give us just 2. And so at the end of the day, the value for the original integral is just equal to 2. I didn't evaluate the integral as it was given before in terms of the x and y coordinates, but I'm assuming that the integral is more difficult to evaluate using x and y coordinates as opposed to u and v coordinates. But you'll see in the example that we have below here, sometimes it might actually be impossible to do the integral in x and y coordinates without a transformation, or at least very, very difficult. And so we'll get to that example next. Okay, so finally we can move on to the last example for this first half of section 15.8. And we want to evaluate the integral from 1 to 2 of the integral from 1 over y to y of the square root of y divided by x times e to the square root of xy dx dy. And evaluating this integral without doing some kind of trick here, I would assume is at least very difficult. Again, I didn't mess around with it and see if it can be done, but it looks pretty bad. I don't really want to mess with it. But maybe we can use a transformation and get rid of the square roots that are showing up inside of the integral and make this thing look a little bit nicer. So we can let u equal the square root of xy, and we can let v equal the square root of y divided by x, and this will actually define for us some transformations between the uv plane and the xy plane. So we're setting some relationships between the variables u and v and the variables x and y, in the goal or in the hopes that when we're done with all of this calculation, when we plug in u and v for the associated y and x terms inside of our function, we get an integral that's easier to evaluate. And it ends up that we do get an integral that's significantly easier to evaluate. So because u equals the square root of xy, we can then say that u squared is equal to xy, and we can say that v squared is equal to y divided by x. So we're just squaring both of these relations we just made. So this implies that y is equal to x times v squared. So we're just doing a little bit of algebra here. And then some substitution. We get u squared is equal to x squared times v squared. Divide by v squared, and we get ultimately that x is equal to u divided by v. So all of these steps in between here is just taking these equations here and doing some algebra until we can solve for x in terms of u and v. And this is the case as long as u and v are greater than 0, because we did have to take the square root right here. So we're assuming that these values are greater than 0, but it is the case they're greater than 0 because, as we'll see when we sketch, everything is happening inside of the first quadrant here. Also, we have v squared is equal to y divided by u over v now. So we've just taken x and substituted u over v. And ultimately, doing a little bit more algebra, we get that y is equal to u times v. Again, as long as u, v are greater than 0, which they are. And so now we have transformations. We have functions in the variables u and v that are describing the variables x and y. And so we can use this coordinate transformation and hopefully get a nicer integral. So the first thing to do now is to sketch the original region R in the xy plane, just using the iterated integral that we have from above. So we have that the lower limit for x is going to be 1 over y, and the upper limit for x is going to be y. Another way to say that is we have the hyperbola y equals 1 over x. That's going to be the, well, we draw that inside of our xy plane, so I draw that in red here. And then we have the line y equals x in green, and we also we also have the lines y equals 1 and y equals 2 because those are the upper and lower limits for y inside of the region R. And then the region R is going to be that region bounded by these different lines that have been drawn now. So it's the region in blue there. And after we have that sketch, we also want to sketch the corresponding region G in the UV plane using our transformations, x equals u over v and y equals u times v. So we start off with this hyperbola, y equals 1 over x. And again, we can just substitute using the transformations. We get u times v is equal to v divided by u. Ultimately, we get u squared is equal to 1, which just means that u is equal to 1 because u and v are greater than 0. And then we have the line y equals x. Again, we do the same kind of substitution here. And we get that v squared is equal to 1, which implies that v is equal to 1. So I'll put squares around this because these are the corresponding curves in the UV plane that correspond to these curves that I have drawn up in the XY plane with respect to the transformation. So we have that the line y equals 1 goes to uv equals 1, which is just v equals 1 over u. So the line y equals 1 is actually going to go to a hyperbola, and the line y equals 2 is also going to go to a hyperbola. So the line y equals 2 goes to the hyperbola v equals 2 over u. The line y equals 1 goes to the hyperbola v equals 1 over u. I didn't draw v equals 1 over u inside of the UV plane here because it actually didn't add anything to the region we're talking about. But the region now in the G, or in the UV plane, the region G, is going to be this blue region that's bounded by u equals 1, v equals 1, and the hyperbola v equals 2 divided by u. Okay, so finally we have sketches of our region in the UV plane now, and so the goal is going to be to find the limits of integration for this new region G in the UV plane, and we also need to calculate our Jacobian and then set up our final integral. Okay, so remember, x is equal to u over v and y is equal to u times v. These are the transformations that we're using. So we take all the different partial derivatives here. Partial x with respect to u is going to be equal to 1 over v. Partial y with respect to u is going to be equal to v. Partial x with respect to v is equal to negative u over v squared, and partial y with respect to v is equal to u. Again, you can stop the video and verify that all these partial derivatives are correct, but they shouldn't be too difficult to calculate. And then we can set up the matrix giving us our Jacobian. So we have this following 2 by 2 matrix right here, and we take the determinant of that matrix, and ultimately that determinant is going to be equal to 2 times u over v. Again, because u and v are greater than or equal to 0, the absolute value of the Jacobian here it's still going to just equal 2 times u over v. So we don't have to worry about any absolute value signs. And finally, we can rewrite the integral from the beginning of this problem here. So we have this integral that was originally given to us, and now we want to rewrite it in terms of u and v and the region G in the UV plane. Okay, so we are going to integrate with respect to v first and with respect to u second. So to find the limits of integration for v, we can draw lines that go up through our region like this and determine when those lines are entering the region G and when they're leaving. So they're entering along v equals 1 and they're exiting along v equals 2 over u. So that gives us our limits of integration for v. And then for the limits of integration for u, we see that the region starts at u equals 1 and it ends at u equals 2. So we have 1 as the lower limit and 2 as the upper limit. And finally, we take our function, this square root of y over x monstrosity over here, and we can rewrite that function in terms of u and v. So that's just v times e to the u based on how we defined v and u. And we multiply by the Jacobian, which is 2 times u divided by v. And so finally, now it just comes down to calculating this new integral with respect to the variables u and v. So first we start off with the inner integral, and we get this 2 times v times u times e to the u from 1 to 2 divided by u. And we can plug in 2 divided by u and subtract what we get when we plug in 1, and we get this 4 times e to the u minus 2 times u times e to the u. And now we're taking the integral from 1 to 2 of this expression with respect to u. I split it up into 2 different integrals because the second part of the integral, this minus 2 times u times e to the u, will require some integration by parts. So the first part, this 4 times the integral from 1 to 2 of e to the u du, will be equal to 4 times e squared minus e ultimately. So this is a very simple integral here to calculate. And then secondly, we have this 2 times the integral from 1 to 2 u times e to the u du. And for this, we're going to need some integration by parts. So the variable u is already taken, unfortunately. So we're going to use some different variables. I chose s and t. So we let s equal u, and then ds is going to be equal to du. We let dt equal e to the u, so that t is equal to e times u. And again, integration by parts gives us 2 times u times e to the u minus the integral from e to the u du, evaluated from 1 to 2. And we do some more calculation here, and this ends up equaling 2 times e squared. And so ultimately, this original monstrous looking double integral that we have right here, after we do the substitution, turns into an integral that we can actually evaluate pretty comfortably. And we get this 4 times e squared minus e minus 2e squared. And then simplifying a little bit, we get down to 2e squared minus 4 times e. And so that would be the value for this original definite integral. So hopefully this last example can show you a little bit of the power of substitution, even though I do admit that the process can be tedious and long, and sometimes finding the right transformation isn't super easy either. But hopefully you'll get some practice with this kind of stuff while you're doing homework, and that homework is up on Blackboard now. So other than that, just look out for the second half of section 15.8, which I'll be putting up on YouTube sometime later today, most likely.